Okay, team, back for the last one here. So we're up to the reactivity exam. So I'll attempt to go through as quick as I can again. Right, so the first question in this one is all about reaction rates. And our first question here is we have to show on the graph how the volume of gas will change for the reaction in test tube C. So test tube C, we have compared to A, we've got the same concentration. Test tube C is chunks, so that's going to be slower. However, you've just broken up the same amount, so it's going to end at the same place. So you'd be expected to do something like this: slower, 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 ending at the same place. Okay, so quite a few of you got that. And then we need to write our explanation. So our key idea is that it's a solid that we're crushing up into small pieces. And what that does, of course, is it increases the surface area, right? So that's sometimes people get that the wrong way around. So smaller pieces have a larger surface area. A key idea here is that with a larger surface area, we have more exposed reactant particles. Please try and talk about reactant particles, and this word here is a key word. So if we have more exposed reactant particles, we are going to get more collisions between our reactant particles. In less time. Right, so those collisions are going to happen quicker. So that key phrase that we like to put at the end is more successful collisions per second. Collisions, or a higher frequency of successful collisions. Right, the next one, test tube B, compared to test tube A. And so if we look at B and A, they've both got granules, but we've got a different concentration. So B has a higher concentration, so we need to identify B has a higher concentration than A. And that means, and it's sulfuric acid, that means that B has more sulfuric acid reactant particles, and this was the key bit, per litre or per volume or per mil, any measure of volume, and lots of you missed that out. And this means that there is going to be more collisions in the same amount of time, or a higher frequency of effective collisions. Frequency of effective or successful collisions. And remember, an effective or successful collision equals a product making collision. So that is, remember we learnt this last year, a collision that has enough energy and is in the correct orientation. But if you have more collisions, you will get more successful collisions. Okay, that's the second bit. And then the third one here. So a new one is test tube D. So we're having the same as test tube C, but we've got a warm water bath. Right, so this one is an increased temperature. Now please, you only have to explain one of them, either the increased one or the decreased one. So I'm just going to go for the increase. So the one that has the increased temperature, which is D, increased temperature in D. So we know that the reactant particles, keep talking about those particles, gain kinetic energy and move faster. So there are two reasons this increases our rate. One, faster moving particles collide more frequently, more often. And two, particles with more energy are more likely to have enough energy energy to overcome that activation barrier. That's the minimum amount of energy you need to make a successful collision. So putting those two together, we've got more collisions in the same amount of time, and more of the particles have enough energy to successfully react. We've given the particles more energy. This does not reduce activation energy. That's your catalyst. So no. And please always finish with a higher frequency of effective collisions or more effective collisions per second. Okay, boom, done. Question 2. Blah, 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 blah. Circle the correct KC. So our key idea here is that carbon is a solid. We do not include solids in our equilibrium constant expression, so that is wrong and this is correct. And our explained choice is just saying that we do not include solids, so we don't include carbon. Okay, on to the next page. Right, so this is a calculation. Actually, everyone did this reasonably well. A few of you missed where to put this. So they've actually got the equation for you. This number goes in here. This number is NO, so that goes in here. And you've got Cl2, so that number goes in there. And this is the number you're trying to calculate. So your expression should look like this. 1.6 times 10 to the minus 5, that's that number in there, equals 5.87 times 10 to the minus 3 squared, that's that one there, times 9.54 times 10 to the minus 3 over x squared, because that's the one we're trying to find out. So what I'm going to do is I'm going to take this x squared and multiply it up to there. I think you guys do a swapsy thing. And this one I'm going to divide back there. So x squared is going to equal 5.87 times 10 to the minus 3. Don't forget to square that. Times 9.54 times 10 to the minus 3 over 1.6 times 10 to the minus 5. So that's what we should have. So if you do that squared times that divided by that, and then you square root it to find x, and the answer that you get, and I just need to quickly look that up now. Come on. So I don't have to actually do it on my calculator right now. It gives you 0.143 moles per litre. So sometimes if you put this in these standard form numbers into your calculator wrong, you can get a weird number. So I suggest you put this in by going 5.87 EXP, right? Use the EXP button and then just put a -3 in. Don't do all that times 10 and do that little arrow lifting thing. I don't know. Just use your exponent button. Okay, over here, the next one, when the temperature is increased to 40, so it's an increase, the Kc increases. And we need to say if this reaction is exo or endo. So if Kc increases, we know we are making more products. Okay, more products, and that's because Kc equals products over reactants in very broad terms. So if the Kc increases, we know that equals a shift to the right to make more products. Okay, so that's our first piece of evidence. Second piece of evidence, if we increase the temperature, the system responds to decrease the temperature or absorb heat, decrease temp, and it does this by moving in the endo direction. Okay, so the endothermic direction absorbs heat and decreases the temperature. Right, so what did we see? We saw a shift to the right. What do we know should happen if we increase temperature? The system should shift to the endothermic direction. Therefore, the forward or right direction is endothermic. You needed to state those pieces of information quite clearly there. That was a hard thinking one. Okay, this one was done quite well. So we've got an equilibrium here. We know that NOCl is yellow, so I'm just going to put yellow on here. So I suggest you write the colours above your substances. Those two are both colourless, essentially. It does, yeah, I mean, I know chlorine's a bit coloured, but you can't really see it. So if we increase the pressure, the system is going to respond. Right, I'm just going to bullet point this. The system responds to decrease this pressure. Can we try to avoid using wants to, likes to, or anything like that to decrease pressure? Now, this is a key sentence here. How does it do this? By moving in the direction with fewer moles of gas particles. Okay, so you need to have that sentence in there. To decrease the pressure, you're going to move in the direction with least moles of gas. So coming back up here, the left-hand side has 2. The right-hand side has 2 plus 1 is 3. So this side has the least. So I would write all that information in. I would write that the left-hand side has 2 and the right-hand side has 3. So we're going to get a shift to the left. What's the question asking? Blah, 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 blah. How the colour will change. Right, the only thing that is coloured is this yellow thing here. So the only thing we're going to worry about is, are we going to see more of this or less of this? If we're moving to the left, left is going to make more yellow. So we want to say darker yellow, and we want to link that to NOCl increasing in its concentration because we're moving to the left. Okay, looking at this one, Cl2 is removed. So if we remove Cl2, we are decreasing the concentration of Cl2. So the system will respond to increase the concentration of Cl2. So which direction is going to make more Cl2? It's going to be the right direction. Move to the right to make more Cl2. And as we're moving to the right, that's going to decrease. We're moving away from the yellow. So we're going to see a lighter yellow. As we are decreasing the concentration of NOCl, right? It doesn't matter about the Cl2. If we want to say what we're going to observe, we must only talk about the coloured substance. Okay. And the third question, this one here, we were pretty bad with our charges. So we've got HCO3 minus, and it's acting as an acid, so it's going to be donating a proton. Acting as a base, it's going to be accepting a proton. And please remember that a proton is an H+. Okay, so I'm going to take that H off and leave CO3. And it already was a minus, and I'm removing another positive charge, so it's going to be 2 minus. That should look familiar to you, right? You shouldn't be getting anything that looks totally weird. You've seen the carbonate ion before, and I'm going to add that to make an H3O+, and I should know that acids make H3O+. That should not be a surprise to me. Other way around, I'm going to take HCO3, and I'm going to add another H to it to make H2CO3. And it started off as a negative, and I'm adding a positive, so now I've got no charge. And I'm taking away an H, leaving OH, taking away a charge, leaving a negative charge. Right, so that should be straightforward. So quite a few of you got to just make sure you check your charges, please. Conjugate acid-base pair is 2 species related by a proton. which is an H plus. Okay, so up here, we've got that and that, right? So the only difference between the CO3 2 minus and HCO3 minus is 1 H plus, or you could put H2O and H3O plus, or you could put H2CO3 and HCO3 minus, or you could put H2O and OH minus. So there are 4 possible conjugate acid-base pairs to use as your examples there. Okay, the calculations here, they were pretty well done. In fact, the only thing I would add to what I saw for this is that you need to make sure your answers have 3 significant figures and units. So these square brackets are concentration, so this has got to be moles per litre. So in this case, your first answer was 1.58 times 10 to the power of negative 12 moles per litre. And the OH minus was 6.31 times 10 to the minus 3 moles per litre. And then the pH up this side was 1.04, but we do not need any units for that. I haven't done the working. You can have a look at the mark schedule to see the working. You don't need me to go through it again here. I would rather spend my time on this doozy here. Okay, so we did need to do a little bit of memorising here. So we do need to know what these 3 things are. So luckily that acid is quite a big hint there. So pretty much everybody picked that Z with the lowest pH must be the acid HNO3, which is correct. These 2 here, ammonia and ammonium chloride, did worry people. So NH3 is ammonia, that is a base. There is only 1 basic pH, so that must be X. And this thing here must be Y. Y is obviously an acid, so that's a little bit of a clue here. And we'll have a look at why that is now. So you need to justify your choices, talking about the pH and the amount of hydronium ions. Pretty standard question. You need to include relevant balanced chemical equations, and that's where we're going to start, because that's going to give us all of our answers that we're going to write. So let's start with X. It's base. Don't just look at the pH and assume it's a strong base. 11.1 is not that high. It is actually a weak base. Ammonia is a weak base. So we're going to add that to water. We're going to make an equilibrium arrow, and that's going to give us NH4 plus OH minus. HNO3 is a strong acid, so HNO3 plus H2O, strong single arrow. It goes to NO3 minus plus H3O plus. Lots of people got that. Some people decided that was an acid and did a weird one there. I mean, these are common species that you should see. If you'd made this an acid, I'm just going to go up here, you would have done this as your equation. You would have gone a proton donating, and you would have gone NH2 minus, and you would have gone, hopefully you would have gone, I've never seen that before. That looks weird. I don't know if that's right. And you trust your instincts, that's not right. So actually you should have tried that as a base if you hadn't remembered it. The last one is a salt. So for that one, and lots of people actually remembered to do this, your first equation for a salt is it fully dissociating into its 2 ions. And if we needed to explain conductivity, we would have done that there. And then this ion is the one that reacts with water in an equilibrium to make that and that. Okay, so now that we've got these, we can actually use these to answer this question. Okay, so NH3, its pH is 11.1. So NH3 is a weak base, which only partially reacts with water. So it produces OH minus. So it does have OH minus greater than H3O plus. So its pH is greater than 7. But because it's weak, it's not like 14 or anything like that. This is a strong acid. So we know it's producing H3O plus, which has got to be greater than OH minus because it's produced. We know it's a lot of it is produced, so therefore we are going to have a very low pH of 1.02. This one here, we know it fully dissociates into these two ions. We then know that this ion reacts with water in an equilibrium, so it's producing H3O+. So it's H3O+ is greater than OH-, but because this is an equilibrium, that imbalance there is not going to be as great as that one there. So because this has got less H3O+ than this, its pH is still going to be acidic, but not as acidic as the strong acid. That's pretty much it. So use your equations again to explain your answers. Boom, done. All right, team, I'm out now. That's only 20 minutes on that one, so I'm quite pleased with that. So have a happy holiday. And if you get to the end here, make sure that you look after yourselves, because we've got a pretty busy term next term, term 4, and have a fabulous holiday. Take care.